Donc, bonjour. Aujourd'hui, je vais vous présenter quelques travaux que vous voyez affichés dans la diapositive que je suis en train de lire en ce moment dans ces semaines. Et la raison pour laquelle je me suis attaquée à ça, c'est parce que je suis en train de travailler sur les concepts de traces et de réputation dans des systèmes multi-agents. Donc, la chose que je voudrais vous présenter, c'est la chose qu'on appelle la subjective logic. Et pour y arriver, il faut passer d'abord par deux autres représentations de la réputation qui sont données par les systèmes basés sur la distribution bêta qui généralisent dans les systèmes basés sur la distribution des Dirichlet. Donc, avant de commencer, je vais vous expliquer quelle était ma question à la base. Ça va être plus facile de comprendre pourquoi j'ai choisi de me diriger vers la logique subjective et quelle partie de la logique subjective je regarde. Et donc, voilà, on y va. Donc, on a un réseau. Dans ces réseaux, vous avez des entités dans les bulles, sont des agents. Et vous avez des entités dans des carrés. Ces entités dans ces carrés sont des items que les agents souhaitent exploiter. Par exemple, dans l'application que j'ai dans la tête, ça va être une information, ça va être un prédicat. Donc, par exemple, il y a un objet dans telle position. L'application que j'envisage, c'est dans le contexte de réseau véhiculaire. Et donc, la première chose qu'on va formaliser, c'est le concept de trace d'un agent envers ces objets qu'il veut utiliser. Donc là, c'est formalisé avec, mieux si je le fais ici, c'est formalisé avec une flèche bleue sur le tableau. Ça signifie que l'agent bleu, l'agent bêta a une observation qui lui permet d'établir sa relation de trace vis-à-vis de l'information X. Et ces niveaux de trace, on va l'encoder comme une quantité réelle entre 0 et 1, tout est normalisé, donc c'est beau. Et on va dire que cette quantité-là, c'est une mesure de la confiance que bêta a dans l'utilisation de cette information. Alpha et gamma n'ont pas de ligne d'arrêt qui connecte à X. Ça veut dire qu'ils n'ont pas d'observation qui leur permettent d'établir une trace dans cette information.
Excuse-moi, Francesca.
Oui.
Quand tu dis que bêta a de l'évidence sur X, ça veut dire que du coup bêta est sûr de X ou qu'il a un indice positif que X est vrai?
Il a observé quelque chose par rapport à X et donc il peut se faire une opinion sur
direct,
X.
Mais pas,
exactement.
Pas à 100%.
Ça peut être à 100%. S'il observe X, il peut avoir un trace de 1 dans X parce qu'il a observé par entier. Peut-être il y a une observation partielle et donc il a que une confiance moindre dans cette proposition, dans cette information.
Du coup, ça peut s'interpréter comme une probabilité.
On va se poser la question et oui, on va utiliser des probabilités.
La question de la langue commence peut-être à se poser. Oui.
I'm going to switch to English.
Okay. I think we already lost someone. But,
sorry. Roll back. In circles, you have agents. In boxes, you have predicates or items agents are interested in using. The first quantity that we have introduced is the trust that an agent has in a predicate or object it intends to use. And so we place in the picture an arrow if this trust is based on some evidence the agent had on this predicate or item. And we call this decision trust because this is the trust that we have in the item we are going to act upon. And then you have another kind of trust. It is the trust that agents have between each other. So in the picture, you have this dashed line between agent alpha and agent beta. It's directed, so this represents the trust that agent alpha has in agent beta. I'm not making the assumption that the that beta should have a trust in alpha if alpha has a trust in beta. So I'm going to call this R, standing for reputation, to make it different from the trust in items. I'm going to suppose it's real between 0 and 1, as before. And as before, if between gamma and beta there is no arrow, it's because gamma never interacted with beta and so has no clue whatsoever on the reputation it should assign to beta. And so I'm going to ask myself a question. The thing that I want to know is, what trust should agent alpha have in object X? Of course, alpha has no direct observation about X, but alpha knows beta, who has some degree of trust in X. So, well, the thing that I guess everybody is thinking is that the trust that alpha has in X should be the product between the trust alpha has in beta and the trust beta has in X. Okay, so this is a solution. Then you can ask yourself the same question, and this time you have a longer chain of trust. But formally, you don't have any difference with respect to the case that we saw just before. So, well, you simply make the product of these three quantities, and then you can say that alpha should have this degree of trust in X. Where things get complicated are in situations like this. Here you have alpha that knows beta, but knows also gamma that knows beta. And so the question is how to determine the trust that alpha has in X. And one solution, at least the first solution I had in mind when I first draw this little example was, well, of course, alpha is going to trust beta in his trust of X. So I'm going to do the same thing as before. I multiply the reputation of beta as seen by alpha with the trust that beta puts in X. But then I realized that maybe alpha knows beta not very well, and maybe gamma knows beta very well, and alpha knows gamma very well. So in this situation, taking the shortest path, it's probably not the best solution because you have more evidence that is associated to this path here. And so this is the motivation behind this reading that I've been doing. I'm trying to find, I'm trying to answer these questions. The first is, how should I represent trust? We said it's a probability. Yes, we are going to take it as a probability. How I should be able to link evidence to these probabilities. How am I going to treat uncertainty? This concept that maybe I'm putting trust in somebody, but I also need to specify how well I know them in order to be able to exploit these trust relations, like this reputation safely. And then how should I treat the transitivity of reputation as in this example here? Okay, so I'm starting from the, yes.
The question, so what would happen if beta as an arrow to alpha? What would you do if the edge would be from beta to alpha would be reversed?
Well, in that case, the only path between alpha and X would be through gamma and beta and X. So
for beta then would, you would do the same. So beta would have beta has the direct path to it. Okay,
yeah. I think in the end, I'm not still done in my application to cutting, well, deciding how to do this, but in the end, I think that when an agent has direct observation about an object, it is going to put, well, to use this as ground truth.
Okay.
Yeah.
If there would be a cycle, that was my question. If there
yes.
would be a cycle in the,
it's an excellent question.
Mm-hmm.
I'm going to get there later on. Subjective logic doesn't solve that completely, there is somebody who took subjective logic and pointed out this problem and proposed another solution that I'm not going to discuss today because there will be no time and I'm not done reading it yet. But yes, this is the problem. And the way out of this problem is to be able to account for any piece of evidence that flows in the graph, in the path that you are choosing to establish your final confidence. So, okay, spoiler for the end of the thing. So to get there step by step, the first thing is representation of trust. I'm going to focus on representation of reputation, but representation of trust will be the same. And the first thing I did was a very, very simple thing. I called it naive binary reputation system because it's naive. Every agent interacts, and at the end of an interaction, it can rate the interaction as good or bad. So binary because we have only two choices. So how we are going to model the outcome of an interaction, we are going to take a Bernoulli variable. This Bernoulli variable has a parameter Q, which is Q of theta. It means this is the parameter of agent theta. This parameter is not going to change in time, so I repeat my experiments, and I can note somewhere how many good and how many bad interactions I had with this agent. So I need to represent reputation, and naturally the thing that comes to my mind is that this parameter beta, Q, this Bernoulli parameter encodes how the level I trust I should put in this agent. So what I'm going to do to represent the reputation of the agent, I'm going to estimate Q of theta. And I'm going to take the estimate of Q of theta as my reputation. So the estimate at time t means that it is the estimate that I can make having at my disposal all the observations that I gathered up to time t. And so, well, this is trivial. So I have ng observation of good interactions, nb observations of bad interactions. So I can write the likelihood of having ng and b observations. I can do my maximum likelihood estimate, and I find out that the parameter that I'm going to use as my reputation indicator is the average number of good interactions that I had with any agent. So this is quite basic as we said. We can do better than this, and we do this with the beta reputation system. So the assumptions stay the same. I have a binary set for rating the interactions, and then I still assume that the outcome is a Bernoulli variable distributed with a parameter Q, which is proper of the agent. But now I'm going to assume that this parameter is a random variable itself. And so what do? I assign a probability density function to this parameter, and the probability density function is the beta density function that you have here in the formula. So it's defined on Q between 0 and 1, so everything is fine. It depends on two parameters, which are this alpha 0 here and this beta 0 here, which need to be, well, positive. And these two parameters select one probability density function in the family of the beta probability density functions. So I plotted the sum here. The thing that I forgot to say is that you are going to choose these two parameters as to encode your prior knowledge on the distribution of these Bernoulli parameter. So, well, you take the blue line, alpha 0 is equal to 1 and beta 0 is equal to 1, you get the uniform distribution. So basically, I have no prior information whatsoever on the distribution of Q. Then you take the green one. So alpha 0 is 5 and beta 0 is 5. You have this distribution here, which I might use if I think that my agents are not likely to be correct all the time or wrong all the time. Okay, so maybe I'm going at the beginning to put more weight in the middle of the distribution, but I'm going to exclude the fact that an agent may be correct all the time or wrong all the time. And the red one, 0.5 and 0.5 does the opposite. So I'm going to put a lot of mass at the beginning on the fact that the agent is always right or always wrong, and less mass on the fact that this parameter Q is in between. So this is how I understand I can tweak my system to encode prior knowledge that I have on the behavior of the agents.
Yes. Just out of curiosity, about the bad or good behavior of the agents, do you think more of purposely bad behavior like Byzantine agents, or do you think of agents that have bad measurement instruments, for example? And
I think this prior here is for honest agents that may be wrong because, yeah, that's life.
But for your application, I meant what is your fear? You fear people who have bad tools, or
no, for the time
behave
being
in a bad way?
No. For the time being, I'm trying to establish a baseline of how things go when everybody is playing nice.
Okay.
And then I will try to see how to attack the system. But for the time being, I'm assuming that everybody is playing nice. Okay. So they might be wrong because maybe they are sensing stuff with noise. And so their belief in the world are not perfect because, yeah, but not because of attacks. Not yet. Yes.
Very difficulty that underlying there is a graph, say an acyclic graph with agents and values and variables.
Yes.
And that the edges are weighted by
I'm not there yet.
Oh, okay.
So my problem is exactly how I should weight the edges and how I should combine reputations when I'm building a path in my graph. But before getting there, I need to get the right representation for the reputation. And this is not going to be what brings me there, but it's building. Yeah.
Francesca?
Yes.
Question. So I don't know if I am like rushing a bit things, but actually, when you use the beta prior,
yes,
then you would be able like to update the posterior, etc.
Yes.
But this will be very similar to the maximum likelihood.
Yes, but not.
Exactly. But yeah, what has to do exactly with the alpha 0 and the beta 0? So I was just wondering how sensitive. I think the systems will be very sensitive with regards to the prior distribution, right?
It can be, yes, but then the prior distribution, I think you should use it to encode the knowledge that you have about the system. And if you don't have any knowledge about the system, take a uniform prior and
so how do you think this knowledge can be available?
Okay, I have one idea with respect to the application. I'm studying, and in that application is vehicular networks. So vehicles are emitting messages, and they are emitting messages about the world. And sometimes it happens that you are close enough to the vehicle, and so you can verify if what they are saying is correct or not. So this is the idea I have in the back of my mind for my application. But defining what is an interaction and what is a good and bad interaction is application dependent. So I have an idea for one specific application, but
yeah, and another thing is, for example, that you show in this plot that when you have the green curve, you put like alpha 0 equal to beta 0, which is 5, 5. But then if you put it 0, 5, 0, 5, this changes completely the result.
Yeah, because you have this 1, 1, which is here. So if you choose parameters which are below 1, you get this funny thing.
Yeah.
I did some Python plotting, changing the parameters. That's as far as it goes.
So yeah, so that means that the amplitude of alpha 0 and beta 0 is also important.
Yes, it is. It is. But then once again, you will choose this alpha 0 and beta 0 once you have an application and once you have some idea about what the behavior of your agents looks like or is reasonably looking like. For the purposes of this talk, we keep it to uniform, and because we do not know anything, but I just wanted to show that these priors can encode information, right? Which is sensibly better than the maximum likelihood solution. But let me skip ahead 3 or 4 slides and we will get back to comparing the two, okay? So yeah, this is the prior. Of course, you get observations as you go and interact with agents. And then you can evaluate your posterior distribution of your parameter Q, and you do it using Bayes. So it's rather simple, and you find out that you are still representing Q with a beta distribution. This time, your two parameters are alpha 0 plus the number of good observations that you had, and beta 0 plus the number of bad observations that you had. So if I started with a uniform and in between I made 8 good observations and 2 bad observations, I end up with a posterior that looks like this. So I encoded the fact that I believe my agent is acting good. Yes, we were here. So we have this distribution, and this we said. So I'm left with my problem of representing my reputation score. So I said at the beginning that I want a score. Reputation, I can represent it with the whole PDF, but I'm interested in a scalar because it will be easier, for example, to compare reputations of 2 agents if I have scalars to compare. So what I'm going to take the expectation of the beta distribution, and the expectation of the beta distribution is very easy. It depends only on the number of observations that the good and bad that I made so far. So I'm happy, and I'm going to fit this.
So here it's a global reputation.
Here is the reputation that alpha has in theta after having observed NG good interactions.
Observed by alpha.
Yes. So usually all this machinery is used in systems where you have a central authority that pulls all the observations for everybody, evaluates a reputation score, which is distributed to everybody. Okay. This is what happens when you rate your restaurant on an application. Here, I'm interested in something which is distributed. Mm-hmm. So everybody has their own assessment, and the reputation of theta as seen by alpha may be different from the reputation of theta as seen by beta, unless we decide that we do some consensus, but we are not there yet. So for the time being, this reputation depends only on the interactions I myself had with that specific party. Okay, so coming back to what we were saying before, I want to compare what I did before with the naive ML solution and what I got with the beta reputation score. And the only difference between the two is that I have a prior. And so when I compare the two scores that I took to represent the reputation, I see that in the ML solution, well, I'm accounting just for the observations. So if I met somebody once and the interaction was good, I'm going to assume this guy is 100% trustworthy, okay? Which is not what I should do, because it's very important to me, the fact that my assessment is based on very few elements, not enough evidence, okay? And when I put a prior, well, what I'm doing, my reputation score with only just one good interaction would be 2/3, assuming uniform prior distribution. And this is much better because having the prior allows me to gather evidence to approach maximum trust, but never to hit this maximum trust. So if I have enough observations, the two things are completely the same. But in the application that I'm thinking about, I'm not going ever to be in this regime. So what I need is something that allows me to encode the fact that there is uncertainty in my result. So this thing of having a prior kind of does this, but it's not, yeah, okay. We leave it here for the moment. And so, of course, this thing generalizes to the case when you want to rate using a set which has a bigger cardinality than 2. Okay, so I called it rating with stars because it's like when you go to a restaurant and then you give your rating. And well, things are the same. You use the Dirichlet family of probability density functions that it allows you to multivariate. So your parameter is not a parameter anymore, it's a vector of k parameters. And so you want to express the probability distribution that, that each of these elements has. So yeah, okay, this is a complete generalization of the previous case, and you have this summation that goes to 1, meaning that either you rate 1 star, 2 stars, 3 stars, you don't rate 2 stars and 5 stars at the same time.
I just have a question.
Yes.
Can we, I don't know too much about this kind of modeling. Can we have, can we go further with having the parameter curve going to infinity, and then do we have something, some continuous density probability?
The treatment of this thing is discrete in nature, in the sense that you have a multivariate vector, but I don't know if you can take this k go to infinity. In any case, you can make it as big as you want. The problem is that when you score this thing, of course, the thing that you need to work with is still a vector. Probability that next interaction will be 1 star, 2 stars, 3 stars, 4 stars. So if you let it go too long, if you let it grow too much, it won't be very useful. Yeah, no, but yeah, there is a very good point that is.
You can give a notation that is continuous.
Yeah, but there is a very good point hidden there, and it's the fact that when you rate agents, you want to be able to compare agents between each other. So the only way to compare them would be, okay, what is the probability that you are 4 stars and above? So you boil down to a scalar thing. Well, yes, sorry, I got carried away. Okay, so this is just to say that it generalizes to more dimensions, but I will stick with binary rating today. So what time is it? How long have I been? Okay. So this brings us to the topic that I started to look at, which is subjective logic. And I was drawn to it because it is a formalism that allows you to work with probability estimates and uncertainty in an explicit way. So it seemed to me that it was necessary for my specific application due to the fact that the amount of evidence related to each judgment will be small. It seemed to me very important to be able to encode this level of uncertainty. So I'm going to use subjective logic in the context of repetition schemes. In reality, this is a wider subject that I do not master completely. So, well, take it for what it is. It's work in progress. And so what is the ingredient of subjective logic? It's opinions, which are those mathematical objects that I use to represent at the same time beliefs and uncertainty in beliefs. And these opinions, these mathematical objects, can be seen or can be derived as a mapping from the beta in the case of a binary, or the Dirichlet probability density function. And this is the path that I'm taking, because this is how I understand it. And then subjective logic as a whole is the formalism that is invented or put in place to be able to manipulate opinions, to combine them, and finally to, I don't know, make a path, this path in the graph that combines the opinions across the edges. Okay, so binomial opinions. Binomial opinions are mathematical objects expressed on a binomial frame, which is a frame of two elements. Here you have element X and element not X. We are subjective logic is a logic, so we are going to express beliefs about events and their complements. Okay, so you can see the frame as the set of states upon which we want to define our opinions. Okay, so for us, we are going to work with repetition. So my frame is good agent, bad agent. An opinion itself, this opinion omega on the state X, is a vector of 4 elements. So the first is the belief. This is the belief mass, defined as the belief mass in support of state X being true. And this belief mass needs to come from evidence, okay? This is not a priori, this is something that I believe because I observed evidence. This belief is the same thing, but in support of the fact that X is false. And then you have uncertainty, which is defined as the amount of uncommitted belief mass. So you have this equation here. You have your belief plus this belief plus uncertainty should sum to 1. Okay. In classical probability, you have uncertainty equal to 0. So of course, belief plus this belief sums to 1. Here you have this thing that when you increase your belief, you should decrease your uncertainty, and the other way around. And then you have the fourth parameter, which is the base rate, which is the a priori belief in state X in absence of any observation whatsoever. Okay, so this is our prior. This would be the prior belief in a standard system. So yeah, when you work with opinions, you might have belief equal to 1. It means that X is true. This belief equal to 1, it means that X is false. When you have belief plus this belief equal to 1, you don't have any uncertainty. And so this formalism falls back to reasoning with beliefs in the classical sense. When you have belief plus this belief smaller than 1, well, you have some uncertainty. So you have this U, which is strictly positive. And then when you have U equal to 1 or belief plus disbelief equal to 0, you have total uncertainty. So your belief is equal to your prior belief, and that's it. Yes, I forgot to say that all of these are in the interval 0, 1, but yeah. And then you have this quantity here defined with the same symbol of an expectation that is called in the book by the author probability projection on the proposition X. This is the equivalent of the belief when you do standard probabilistic reasoning. So this is defined as the belief plus the prior times the uncertainty that you have on the state. And so this is the scalar quantity that we are going to use to represent the reputation of the agents. Yes, so as I said before, you can realize a mapping between the beta reputation, well, the beta PDF and the binomial opinion, and this mapping is quite easy. So this is to convince myself. This was to convince myself that the two things were somehow a different way to observe the same process. So here you have the beta PDF, and here the first thing that I'm going to evaluate is the base rate, so the a priori belief in my opinion omega. And my a priori belief, I know what is. It's this quantity here. And so, well, my a priori knowledge is characterized still by two parameters. So I have this parameter alpha A here, and this parameter W here, which is alpha 0 plus beta 0. And so I'm going to define my belief in something as the number of good in event X as the number of observations that confirm X over this denominator here, that this belief is the number of observations that invalidate X over the same denominator. The uncertainty is this quantity here. So I have this W, which is a parameter of my a priori belief. And then if I sum the three, of course, NG plus NB plus W, I get 1. Okay, so here you see that as NG goes up, my belief goes up and my uncertainty goes down, as it should be. And I have a well-behaved system. And then I'm going to evaluate my probability projection of the opinion with the formula that I said before. And then you get this result here, which is the same result as the expectation of the beta PDF. So beforehand, I was using the expectation of the beta PDF as my reputation score. I found it perfectly good in an intuitive sense. And now I'm using the same score, which has the same exact dependence on the priors and on the observations as my reputation score. Okay, so we are nearly done. This is, well, this concludes my representation of the reputation of the agent's problem. I have a mathematical object to represent them, and then I'm going to use subjective logic to combine. Well, subjective logic allows me to combine opinions, and then I can take this projected probability projection of combined opinions to combine reputation scores. So I put here a table of all the operations that are defined on opinions by subjective logic. Of course, they are a lot. So I'm going to pick a few examples. Well, the first one is, I chose it just to show you the logic aspect of subjective logic. And well, it's kind of a silly game, but I imagined, what if I want to build a reputation system for all my colleagues? And of course, I'm going to want to take into account different aspects for people, than good or bad. So I don't know, I decided that I want to rate my colleagues depending on whether they are knowledgeable or not in their topic, whether or not they are punctual, and whether or not they are willing to swap classes with me, because it's very important to me. So if I want to build a reputation that depends on those three characteristics, well, I can rate any colleague on each of the three, good or bad, but then I need to have a way to combine them. And subjective logic allows me to form opinions on each of these three frames, and then to combine them with this operation, which is a multiplication operation, or it's a logical AND. And so in the end, I'm taking the probability projection of the opinion that I have on a given colleague, for him being knowledgeable or her punctual and willing to swap classes with me. And so if you go, well, yes.
Small question.
Yeah.
What happens if the frames cannot be considered independent?
Yeah, if the frames cannot be considered independent, this thing doesn't hold. I mean, in the book, it's written that they need to be independent. What happens if they are not? I don't know. The problem is that when you lay down this logic or this formalism to manipulate things, you are doing it in a completely abstract way, and you are not tracking the evidence. So I think in order to solve these problems here, you need to get an application, understand how evidence is collected, and then write down all these formulas, putting the evidence explicitly out, so that you can say, well, this evidence is counted twice. Well, this evidence is not really independent, so it doesn't work in my case. Yes, I think this is the way to go. Yes.
So your three components here that seem to be symmetric. Can you weight them and to give more importance on one characteristic compared to the other? Is it possible, or again, it's just a question?
Probably. No, I'm thinking probably, because this was a very silly example that I picked just to show you that you can do logical ends. I'm not sure that I'm not even sure that you need to have frames with the same number of elements in it. And I don't know. I don't have the answer. Okay, so this was the example to give you the feeling of how it goes. And then, of course, here I put, here I'm combining only two states, yes. This is the result that you get when you make assumptions about the uniform prior. I did this just because these formulas were too big, and so they got more manageable on the board, but of course you can choose A and W as you wish. And this is what happens when your uncertainty is equal to 0. So it's just to show you that if you put the uncertainty equal to 0, this thing boils down to regular reasoning with beliefs. So your probability projection is nothing more than the belief that you have in the composition of these two states. Okay, so now back to my original problems. So here what I have, some observation of alpha and beta. So I have the reputation of alpha of beta as seen by alpha, which is the probability projection of this opinion here. I have a trust of beta in X, which I represent as a probability projection of an opinion as well, because, well, there is no formal difference between the two if I treat opinions. And then what I want is the opinion of alpha, well, the trust of alpha in X, and I can combine these two. And I combine these two using the discounting operator here, which is defined in subjective logic. So I have the combination of the opinions, and I take the probability projection of this. That gives me this quantity here. So you will see that the belief that alpha ends up having on X is the belief that alpha had in beta times the belief that beta had in X. This is our first guess at the beginning of this journey. So it kind of made intuitive sense. So what happens in the complex case, the one I couldn't sort out of intuition alone? Well, in this case, at the beginning, you have alpha has an opinion on beta, alpha, which is this one, alpha has an opinion on gamma, gamma has an opinion on beta. And the first thing that I'm going to do is I'm going to combine the opinion that alpha has on gamma and the opinion that gamma has on beta to get this opinion that alpha has on beta by proxying of gamma. Okay, and I do this with the discounting operator that we saw just before, so I can do that. And so I land in this situation. Now I have this opinion here, this long edge here, and this blue edge here. And so the thing that I want to do now is to combine this edge here and this edge here. And I can do that. Okay, this opinion that alpha has on beta by proxying of gamma, I called it opinion on beta by alpha by proxy of gamma. It's the awful notation, but for the time being, I'm stuck with that. And so I have this consensus operator here. The formulas get very bad. There is a denominator here that I put in this form of kappa here because, yeah, it was simply impossible to put the thing on the slide and to read the thing from the slide. And this quantity here gets very complicated. But then it still it keeps being a function of this belief and uncertainty and A. Yes.
Here. So there's different operators that makes what you want to have.
Yes.
But how do you know the correspondence between them? I suppose that in the book that you read, there is some explanation.
So if you here you have the subjective logic operators, and you have a correspondence.
Where does this correspondence come from?
This comes from the book. And then it comes from the mind of the person who concocted this.
There's some justification for that in the book.
Yes and no. First thing, I didn't look at all of them. And some of them make sense. For example, if you look at the end here, the logical end, you end up having like the belief in X over Y is the product of the two beliefs, plus you have a term which is the belief in X with the uncertainty on Y and the belief in Y with the uncertainty of X. So you have the sense that this belief should take into account both the beliefs and both the uncertainties. How he arrived to this formulation is not always clear. And I'm concluding. There is what I looked more closely are the consensus and the discounting operators, which are the two that I'm using to make this repetition flow in the graph. And these guys here that made this paper, they argue that the formulation of these two operators are not well done, because they kind of make sense if you look at them with the intuition of probabilities and beliefs, but they are not rigorous enough in accounting for the flow of evidence that should pass from edge to edge. So what they propose is a reformulation of these operators, which is done basically with the exercise that we were saying before, rewriting everything in terms of evidence, just to make sure that you are combining things in the proper way. And so this will be this is what I plan to use in the end. But to understand this, there was the step before, and that's it. So finally, here the thing that I managed to do, I managed to combine these two flows of trust in beta from alpha, and once I have this, I'm left with my global trust in beta from alpha and the trust that beta has in X, and so I can combine them to find finally the result I was looking for, and that's it.
Thank you very much.
Yes.
So in this example, since we are discussing trust, if you have two paths, would it make sense to take a maximum of trust?
Two paths between.
Yeah, you have the one from alpha to beta, and you have the gamma alpha to gamma to beta. And so would it make sense to find something which rather than consensus would be more just the maximum trust? To just forget about the weakest trust and just look at the path which leads to the maximum trust. Does it make sense?
The path with maximum trust may be the path with most uncertainty to it. So the best thing for me is to combine the two trusts, but in a clever way. I mean, I want to go and combine them, meaning that I combine all the evidence that I have on gamma. And I think this is.
But in the case where another way of posing the question is that if there is no uncertainty, does the solution, which is they call
if there
consensus, is, does it boil down to the max?
I need to work it out. I didn't work out this formula without the uncertainty, which is really weird, because if you look at the belief and you put because this is a combined uncertainty. So yeah, the thing that I need to do, and I will do it because it's a very good question. I will evaluate everything in this example, and so I need as a first thing to evaluate the combined opinion on this edge, on this combined edge, and see what happens when I don't have uncertainty here and here. So I will end up.
But probably that's not what you want to do, because if you have 80% of trust by one path and 80% of trust by another independent path,
but there is something
say that
wrong.
you have more evidence than in the situation when you have only 80% of trust by one path. See what I mean?
There is something wrong here, because even if I start with no uncertainty here and here, then I'm going to use this formula to combine the two opinions, and I end up with a positive uncertainty, which is the disbelief the disbelief that alpha has on gamma. Yeah, because in this flow of repetition, I end up saying, if I do not trust 100% gamma, the amount of disbelief that I have on gamma, I will consider it as uncertainty on it. I don't know, it doesn't always make intuitive sense. And I agree with you. And that's, once again, the reason, because I'm much more comfortable with the work of these guys, because they take the pain of going back to evidence, and this is something that you are sure that you are doing something sensible when you account evidence instead of these mechanisms. But as I said, it's very much work in progress, so I'm still pondering.
Other questions?
Another question on the statistic estimation with prior and so this would be for individual edges that you would take this thing, right? That the distribution of the sort of quality of the link you would take as a data distribution, and then you iterate that. So, but so if you want that, so are there any stability results when you take the product or things like that?
Yes, there are theorems that look at this, and that I didn't.
For the independent case, so
yeah, I
in
mean,
the past you will have a product and of beta, and then you estimate if you have a single pass, it will be a product of beta.
So I don't know what has been done in the book using priors which are not uniform, because the theorems that I read, they were all assuming prior uniform priors. But then the book is a book. It's very dense, and I don't know exactly how it is treated. Then, to be fair, in the book, he goes with a generalization, like with the Dirichlet. So everything is more complicated because you have vectors everywhere, and sometimes it's not very easy to follow because it gets simply, well, more complex than this. And the theorems are in that case. So most of the time I had to roll back to the binary thing that I can handle more easily in my head for the time being. Yeah, but yes, this is the big problem that I find at this point with this whole theory. It doesn't seem it doesn't seem very well grounded in your intuition when you start combining things, and so you get the feeling that you are not, well, that you cannot check if you are doing it right or not, basically.
Questions? No. I have a question. Will it be possible to imagine that each agent, for example, has a Bayesian network about all the rest of what happens in the system, and updates this Bayesian network each time there is some information or ratings or something like that?
Yes, I saw examples of subjective logic used in those cases, and I didn't look at them because it's not my goal for the time being. So I was trying to
because I don't know Bayesian network very well at all, but I think that at least in the case of Bayesian networks, you will have at your disposal the rules for combining what happens with different paths, and it will solve at least that part of the problem.
Yeah, it's definitely, there is definitely a chapter which is applications on Bayesian networks that I didn't read yet. But yes, this thing can be used in those cases.
Okay.
Yes.
another question. So in this opinion dynamics, there's all this class of models where we do averaging rather than taking the prior.
Averaging to us is this operation here.
So I mean, you probe your neighbors. Assume you have on one thing you want to assess x, right? And so you probe your neighbors.
Yes, I get the opinion.
And so on graphs, it is like the heat equation.
Yeah, it's I mean, what I probe my neighbors for in this moment is their opinions and not their scores. So I can get access to the beta, the belief, the disbelief, the prior and the uncertainty of my neighbor, not just the scalar, this probability projection. If I had just access to their belief, not their belief, their reputation score, I think it would make sense to average. But the problem that I see with that is that if you give me your reputation score, I do not have any explicit information of your uncertainty. And so maybe I'm taking your reputation score, which is not so good, as something which is not so good because the agent you're referring to is bad. And in fact, it just means that you have a lot of uncertainty.
Yeah, they are averaging with weight, and you can discuss for instance, and then I would put some weight with small with even the bigger with somebody else. But on a given graph, you can do averaging. And so I'm just trying to understand.
Yes.
Because these are classical things, these averaging things on opinion dynamics.
Yes.
Have been, so it's reduction. You can reduce it to the heat equation in the graph.
Mm-hmm.
And then the speed of convergence, what it converges to, depending on lots of things have been studied, the speed of convergence. And so I'm trying to see what, so the main novelty is this notion of uncertainty, right?
Yes, and why I'm looking at this with a different angle is that I do not believe in my application I will be ever even close to a situation where I can get consensus or convergence of between agents, because the agents stay together for minimum amounts of time, and they do not get to observe a lot of information either. So those asymptotics are completely forbidden to me. So
or you can look at the transient of the equation and the graph involved. So I mean the consensus in the integration is one thing, but so it's not only the consensus which is written. You can iterate the equation and the graph for certain of steps and see what you get. So,
yes, maybe I will try that.
Sorry.
It's another approach I didn't take, and I should try. Yeah.
Okay, but the main thing, this piece of literature is about this notion of uncertainty, which is in a sense not present in this.
The main thing is that they took the trouble of having a mathematical object that gives you the quantity of uncertainty that you have, which is, once again, you can remap everything on the beta afterwards. So this concept here is still is already embedded in that thing that we observed at the beginning. If you have a prior, you are not putting too much weight on a sufficiently small amount of observations. But there is all like not explicitly expressed. And what I was aiming at is something that allows me to say this agent has more uncertainty than this agent on the same object, on the same target. And so that's why subjective logic. Well, this is the solution that came up in searching for this. Yes?
I have a question. It sounds like the system is like an anarchy system that only people observe the others rather than their authority. But I think in a vehicular network system, if there are certain level of authority like this error 1, error 5, such as
you don't really have an authority when you are. I mean, it depends on the applications, but basically you need to imagine cars going around and shooting out messages. And so other cars may know that there is an obstacle they are not able to observe, okay? And they are going to consume this message without passing through an authority. So the idea is to be able to tag the emitter of the message as a trustworthy or not peer. And the only way that you can do that, if you are not close enough, is to using the opinions of the others.
My point is, based on regulation, if a car is on the road, the regulation should regulate the car to send a message at least at some 99% of reliability. There is no. Not really. in this model.
Not really. If you are, well, first thing, you might be lying because you are attacking, but what happens if you have a sensor that is not working fine and you don't know it? You are going to send out information which is not true. And so your neighbors will be able to spot it. And so they will be able to say this unit here is not sending out reliable information. What I'm working in like the application is how do you protect this network where everybody is supposed to send out good informations, but in reality they are not, against attacks or case where you have malfunctioning.
Yes, I agree that there are some malicious agents, but I mean, in a healthy system, in a real system, there should be some. Take a driving license first. The car take a car driving license first.
Think about autonomous vehicles. Okay, yeah, they will break in some sensor will break at a given moment. Okay, so the thing that you want is to take this thing that is not working properly anymore and take it out of your system. Okay, so if you want, you can imagine that maintaining trust in the other vehicles that you meet is a way to spot the ones that are not working properly, not because of attacks maybe, but because they simply have a failure somewhere.
So in that case, they should even have a trust about themselves. You could imagine that you have also a trust about yourself and about your sensors.
Yes, well, this is actually one of the things that are in the back of my mind, which is, yes, building a system where you share stuff with the others and your aim is not to detect attackers, but it's to do self-diagnose of your system. Because for these applications where you are supposing everybody is automated or tasks are automated, it will be very important to be able to auto-diagnose. But to be fair, nobody is going on the road with systems like this for the time being. So this is like, we are thinking ahead and we are thinking about possible solutions, but you cannot guarantee that everybody will be playing honestly with the use of an authority in a system where messages are sent in a completely decentralized way. It's a specificity of the V2X network where you exchange with your neighbors. Already, if you have an edge, maybe you have more power in controlling what goes around, but when you are doing direct communication, you have this problem of making sure that the information that you get is genuine.
Higher information, like data distribution,
yes,
is a parameter on the network level. Like everyone has the same parameterized data distribution, or it's per node?
In the network that I'm thinking about, not really. Everybody is going to evaluate the trust in the neighbors. So every agent might have a different prior. Every agent might. If you want to start to do consensus or averaging ratings of different agents that comes, well, ratings with respect to the same agent that comes from different parties, probably it does make more sense to have the same prior, because otherwise you will average quantities which are not exactly the same. But in the assumptions that I made, everybody can have their own priors. And yes.